derivatives. Pick up where we left off the other day. The derivative of a function. A single variable chosen value input when it exists is the slope of the tangent line to the graph of the function at that point. And the process to find the derivative of a function is called differentiation. So basically, here's a curve like this. All right, whatever that function might be, that's some type of quadratic function, right? Whatever that might be. So the derivative would be essentially what this line would be at that point. This line at that point. This line at that point, and so on and so forth. All right, so a derivative is a new function that lets you plug in the value of the point and evaluate what the slope of the tangent line, what would be at that point. At the same time, do you ever remember those problems where you throw the ball up in the air? All right, you throw the ball up in the air and you're looking for the acceleration. Obviously, if you throw it up, it's going faster. What happens when you get to the top? Slows down, basically comes to a stop. Then when it starts coming back down, it starts slow and it speeds up as you go, right? All right, and all right, so back to that example I was saying, it's obviously going to have different speeds across it, right? So we will be able to figure out the speed at different times throughout the function, which is, I mean, I think it's really, really cool. You know, when that ball starts, when it's climbing, how fast is it climbing? You know, when does it reach zero and start going down? It's called a point of inflection, where it starts curving down, and those types of things. All right, so the definition of derivative is very, very similar to what we did with just the definition of a tangent line. It's still a limit. We're still going to be working with a limit, but now we just have it kind of in function form. This is in derivative form. Okay, derivative, you would read this f prime, that f apostrophe, f prime of x. So f prime means this is the first derivative. We'll get to something called the second derivative. You would just put 2 up there. Okay, so you would say f prime of x is equal to the limit of f of x plus change in x minus f of x over change in x, or delta x. All right, and that's provided the limit exists. All right, so this is the long way to do derivatives. Okay, we're going to find the derivative of this thing, which is going to be a new function that we could use. Okay, so find the derivative of x to the third plus 2x. First thing, we just want to use the derivative function. All right, f prime of x equals the limit x approaches 0, and we're going to plug stuff in to this thing above. Okay, so we want to put x plus delta x in for x, then just have f of x, put it all over delta x. Same thing as before, we want to try to factor things out, get delta x out of the bottom, so that way I can plug the 0 in and I can evaluate it at that point. All right, so on top, I'm going to end up with, put x plus delta x in for x. So x plus delta x, 3, plus 2 times x plus delta x, minus my function, which is x to the third plus 2x. All right, and then it all goes over delta x. All right, so now I need to start simplifying here, because chances are I'm going to have to simplify, factor some stuff out, cancel some stuff out, those types of things. So let's go ahead and simplify that first, the cube. All right, if I simplify the cube, oh, I didn't pause it, did I? Yeah, I did. All right. So we put that in. Let's expand that first one to expand the cube. So we expand the cube. We have the limit. X approaches 0. I don't know why it's highlighting. And we expand that, which looks like we're going to have x cubed plus 3x squared delta x plus 3x delta x 1 squared plus delta x cubed plus 2x plus 2 delta x minus x cubed minus 2x all over delta x. Now you can expand that however you want. You can expand it by rule, or you could expand it by just foiling twice, however you wish you would do, but that's what you get whenever it comes out. All right, so let's just take a peek here. X cubed is going to be gone here and here. Looks like 2x and 2x is gone. That's about all I can kick out, isn't it? And that leaves me with an x approaches 0 of 3x squared delta x plus 3x delta x squared plus delta x cubed plus 2 delta x. Now, I like where I'm at because I got delta x's all over the place, don't I? So essentially on top, I could factor out a delta x, right? Cancel out here. This guy's gone. This guy's gone. Those are the easy ones. Okay. Now this guy becomes, the 2 goes away. It's just I have 1 left. This goes away. I only have 2 left. With me how I simplified that? Yeah? All right. So then that leaves me then with limit x approaches 0 of 3x squared plus 3x delta x plus delta x squared plus 2. Yep, it's the same as factoring out a delta x on top. All I did was since I took a delta x from the bottom, I took 1 delta x from every single term on top. So in like 3x squared delta x, there's only 1 delta x, so it's gone. Second one, I had 2 delta x's because it was squared, so I took 1 away, leaving 1. The other one I had 3, so I left with 2. All right? Now, I'm to the point now, delta x has gone out of the bottom. Anytime I get to this point and I can plug in that value for my limit for direct substitution where it doesn't give me an illegal answer, I'm good. So if I go ahead and plug this 0 in now for delta x, so it'll be here and here, those are going to cancel out, aren't they? 0 squared is 0. 3x times 0 is going to be 0. So then I'm left with the limit is delta x approaches 0 is going to be 3x squared plus 2. All right, so that function there is a new function that will give me the tangent line at any point throughout that. All right.
So you want to stop whenever you can't combine or?
I stopped when I combined everything I could. The big concept is I want to get to a point where I can factor out a delta x and then cancel in every one of them. I want to try to factor out a delta x, cancel, because as soon as that delta x is out of the bottom, now I can plug my 0 in. All right? And then that leaves me then with this 3x squared plus 2. Now, as we go forward with derivatives, you're going to get rules. And I could tell you looking at this right now, like at the beginning, f of x equals 3 or x to the third plus 2x. After you learn the rules, you can look at that right away and say, all right, it's going to be 3x squared plus 2. All right, you'll be able to do that in 10 seconds. But now this is the concept. This is what we're doing. We're taking those points down. We're trying to get the points of that secant line, just trying to get them as close together as possible. So then that's going to give us the most accurate tangent line for that point. All right, so let's look at another one. Now, again, all I'd have to do too, if I wanted to find the slope of the tangent line at a certain point, I would just plug in, if I had 3, 2, then I would just plug in 3. If I had -5, -1, I plug in a -5 and it would show me. All right, let's keep going.
So say that x the 0, say that was like a 1 or a 2, and you plug it in for the delta x.
You could do it anytime, essentially by limits. That should all be delta x. But the rule of this is always going to be delta x approaches 0. Because we remember the secant lines. Remember I showed that thing yesterday? When you have your secant lines, when they're apart, the closer you get them together, the more accurate your point's going to be, right? Now, as they get closer and closer, that distance between them is getting closer to 0. That's how a limit works. So as that point gets closer and closer to 0, our secant line becomes, or our tangent line becomes more accurate. That's what we're doing. Change in x is taking that point and moving it closer and closer together. So we're trying to get that change as small as possible, and that's why it's approaching 0. Does that make sense? Someone else just walked in a minute ago. Okay. All right, here we go. Let's look on with the square root. Down to 2 left. So using the derivative, find the point at a slope. Find the slope at a point. Set it backwards. First thing we want to do, we want to find the derivative. Then we have 2 points. Okay, so let's just find the derivative first. So I want to find f prime of x. My function here is just square root of x. Okay? So the limit of delta x approaches 0. Plug in x plus delta x for x. So I have x plus delta x inside the root minus f of x all over delta x. All right, so from there, I need to simplify somehow, right? And right now, there's really no way to get that delta x out of the bottom unless I would do the conjugate. Remember doing that with the limits? Multiply by the conjugate if you have something with roots like this. So let's multiply by the conjugate. So I'm going to multiply by root x plus delta x plus root x on top. If I do it to the top, do it to the bottom. Remember, the conjugate is just take whatever you have and change the sign from a plus to a minus. So I'm going to multiply the top and the bottom both by that. Okay? So that's going to make it, on top, I'm just going to be left with x plus delta x after the multiplying the square roots. They're going to cancel out. Then I'm going to have negative root x times the top, and then a positive root x times the top. So those cancel out. And then I'm going to have negative root x times positive root x, which is going to be minus x. Okay, so that got rid of all my roots on top. I'm multiplying by the conjugate. On the bottom, then, I'm just going to have delta x times all this junk. X plus delta x plus root x. Okay. Now, if I look at this, what actually happens is those parentheses are pretty much worthless on top, right? Right? So I'm going to get rid of these parentheses. And what's that do? Well, now my x's are gone, right? So I have a positive x and a negative x, so they're gone. And I also have delta x is the only thing left on top. Delta x is already factored out on the bottom. That's gone. So now I'm left with the limit of delta x approaches 0 is equal to just 1 over x plus delta x plus root x. Now I can plug my 0 in for delta x and be fine. Alright, I plug that 0 in for delta x. Well, I'm going to have x plus delta x, right? So that's going to be equal to limit x delta x approaches 0 of 1 over root x plus root x, because the delta x is gone. Well, root x times root x is going to be what? It's plus. So it's just 2 root x, right? Limit delta x approaches 0 is going to be 1 over 2 root x. Now, what's the only thing that x can't be? Do we have any restrictions? Can't be negatives, yeah. So x has to be greater than 0, right? All right. So there, I got my function. Just a little restriction, just in case. So the first one, I have the point 1, 1. Now, when I'm doing this, I just want to find f prime of my x value. What's my x value on this point? It's 1. Okay, so I want to find f prime of 1. I put f prime of 1 in, I have 1 over 2 square root of 1, which Square root of 1 is 1, so it's going to be 1/2. If I use the 0.42, I only care about my x value. So now I'm going f prime at 4. Plug it in, I have 1 over 2 root 4. Square root of 4 is going to be 2. 2 times 2 is 4. So the slope of that tangent line would be 1/2. At the point x is 1, it would be 1/4 at x is 4. Questions? All right. Still good? All right. Last one. Find the derivative of a function. So I'm going to find the derivative with respect to t for the function y equals 2 over t. So the only reason I did this, I just changed the letters up so you guys don't fall in love with like the delta x thing. All right, this one is just delta t. Okay, so you're going to see this type of formation. If we want to find the derivative, typically a derivative is dy dx. Okay, that means this is a derivative of function y for x is my variable. Okay, that's all dy dx means. It's a function of y with a variable x. Okay, you'll see that written at times at the end of problems, dy dx, especially when we get to integrals. But dy dx just means it's a derivative of function y with variable x. That's all that means. Okay, so in this case, this is a function y, and it would be dt. Okay, now the only reason I don't do that is usually a function is f of x, right? So if I have f of x, I'm finding the derivative, and then it's just f prime of x. This one is not f of x. It's a function of y. Okay, so I can't write f prime. The only way that I can write to show that I'm finding a derivative is to put this dy dt. So that means it's a function of y, well, it's equal to y, and my variable is t. That's all it means. Nothing else changes, though. We're still just looking for the limit. This time it would be the limit as delta t approaches 0. Now, in this case, nothing changes, just t is now x. So we have f of t plus delta t minus f of t over delta t. Okay, it's the same formula, I just have t's in place of it. All right, so the limit, I need to plug in t plus delta t for t minus f of t over delta t. So I get the limit, delta t approaches 0, is going to be 2 over t plus delta t minus 2 over t all over delta t. All right, now in this case, let's find a common denominator for the top. So the common denominator for the top is going to be t over t, or t times t plus delta t. So therefore, I'm going to have to multiply this guy by t, this guy by t plus delta t. Just simplifying radicals like we did before there. It's going to leave me with 2t minus 2t minus 2 delta t. All right, all over t plus delta t, and that's all over delta t. All right, so from there, let's see what we got. So we have this. I can take this guy in the top, 2t and negative 2t cancel out, right? Okay, so then let's come over here, limit delta t approaches 0, I now have negative 2 delta t over t plus delta t. And then that's still all over delta t. Now, let's take this bottom up. I have a single fraction on top. Let's take this bottom up reciprocate, because this would be over 1. So I can do 1 over delta t, right? Multiplication by the top. Flip it, multiply by the top. And I'm going to cancel out my delta t's. Now that's going to leave me with the limit of delta t approaches 0. It's going to be negative 2 over t plus delta t. Now, can I plug a 0 in right now and get away with it? I can, okay? Because I'm still going to have t times t, and then I'll have t times 0. So if I plug that in, that zi in for 0, that's going to leave me with a limit. Delta t approaches 0 is going to be negative 2 over t times t would be t squared, and then plus delta t is 0, t times 0 is 0. So there's my function. That would be my derivative. Questions? Able to follow me there? Okay. All right, so that was just finding the derivative. I put a few of those in your homework. I posted the assignment end of last week. Probably the first half you could have done. The second half you could do now. Yeah. All right, then the last thing here, just the theorem, 2 notes. Theorem 2.1 for calculus says differentiability implies continuity. So if f is differentiable at x equals c, then f is continuous at f equals c. So what's this mean? Basically, if something is differentiable at a point, if you can apply the differentiation at a certain point, that means it's continuous. Remember, this is the last thing we did in pre-calc? But just because it's continuous does not mean you can definitely find the derivative of it at that point. Okay, so if something is differentiable, that means it is continuous. But if you know it's continuous, that does not necessarily mean you can differentiate it. All right, questions? All right, we'll stop right there for this lesson.